Welcome back. I know that last time I mentioned we were going to head into real lambdas, but there is still a little thing that I wanted to cover, and that has to do with templates and function pointers, because there is fundamentally an alternative way to implement what we covered in the last video. And that has to do with really leveraging templates. And I want us to understand really the pros and cons of both approaches. So I'm going to actually show you this piece of code. I realize it's a little small on the slide, but you have the PDF for that. I want instead to actually bring this up in a terminal window and take a close look at this code. It's a completely alternative way of doing it. So let me bring it up inside Emacs. And here's the file. So now we look at the bottom, and this is really our main routine, the one that's at the bottom of the slide. So same story as last time. What I'm doing is that I'm creating a vector of double value, right? Fairly straightforward, lives on the stack, the usual thing. But now when I use find, I do this funny thing where I actually instantiate the function and I say that this find should run with doubles, right? So it's a find for a container of doubles, and it should use the compare function, but this time compare is not an argument of the function, it is an argument of the template instantiation. This is something we've never done yet. And it offers a very specific trade-off in terms of composing functions. Once I get the result, I simply print it out as usual. So that's the one change in the main function, is that this compare that used to be an argument last time is now being moved into a template parameter. That's the first big difference. Now let's see how the implementation changes and really explore the meaning of that as contrasted to the one we saw before. So here is, of course, the compare routine in itself is not changing. You see it up there. There is no need to actually focus too much on it, but this is my find. And the big difference here now is, as expected, template has two arguments, right? The template parameters, there are two of them, and they're different from the function parameters. So the first thing I'd like you to remember is that when we're dealing with templates, we have really two steps. One, we have the template instantiation. That's when you have a function foo that's templated, it's what goes inside the angle bracket. And then the second part is two, we have the function call per se. And that's what goes inside these parentheses, right? That's the important thing to remember. We have a contrast between these two, and it's a good idea to actually remember what that is, okay? So instantiation and function call. That's the first step. I just didn't realize I wrote on the text, so let me just squeeze that a little bit, make it a little smaller. That's where the call goes, right? So that's what's happening. So this is exactly what you see here when I'm defining my function, and when we saw the call in main we had two parameters coming here for the template instantiation, double and compare, and two arguments to the function call coming in here. They are completely different and they play a different role. Before, the second argument, compare, was being passed as an argument over here, and the semantics are completely different. That's what you see in the function definition as well. I have two arguments to the template, a class T, and then this CMP function. And then we have find with another two arguments. So, of course, clearly, the arity of both the template instantiation and the function call do match with the actual usage of the find function. Now, the rest of the implementation that we can look at here is exactly as before. I'm using compare as if it was an argument to the function find. There is nothing special about it. So what gives? What's fundamentally the difference? Well, the difference is that when we are using the instantiation, what you notice is that I instantiate with a type. When I say class T, and actually there are two alternatives. I didn't make this all that explicit, but when you actually are inside a template, you can say class and then some identifier, but you can also say type name. And the class was the only option in the old version of the standard. Type name is a new addition. But fundamentally, the semantics of these two are equivalent. There are only very rare circumstances where you should use type name and not class. So I tend to use them interchangeably in my template definition. So the important thing though is that it means that ID is a type, okay? That's quite different from the second argument where you find a traditional C-like definition of an argument. Compare is not a type, it is a value. So what you can put inside the template instantiation is either types or values. And what we have here is that find is specialized by taking this value, the compare function, and plugging it in at its use site. So we're really blending the two directly when we instantiate the template, which is quite different than passing CMP as an argument to find, because it means then that when the code is compiled, we haven't blended the two functions. It's only when we invoke find that we can pass an actual argument, an actual pointer to a function to have find do its job in tandem with that compare function. So the composition happens at a very different time. One is compile, the other is, the template is compile, and the way we saw before is runtime. Compile time versus runtime. That's what you're getting. But it's kind of interesting. We haven't seen that quite yet. We can use templates for defining types as parameters, but also values. And that's an example of that. So that's the big difference here between the two. If we summarize the trade-off, this is what we're seeing, is that with the C style, you get a runtime composition. You still have function call to compare. With the template style, however, it's a compile time composition. The function CMP is injected directly into find when the code is being compiled. On top of it, if compare has been tagged as an inline function, it can be inlined, replacing the actual call by the body of the function once and for all, which gives you a complete blending of the two, eliminating the function call and having the maximum potential performance out of the resulting code, even though the code in itself, when you read it, is still in a nice traditional function and structured style, separating the concept of finding from the concept of comparison. It's just at the time you instantiate the template that they get blended completely. The big difference is runtime versus compile time. So if you're obsessed about performance and really want to eke out the last bit of it, maybe a compile time composition is the better strategy, and you can actually do that. The point though is that these very simple animals that we've been looking at, pointers to functions, they work equally well in both contexts. You can use them for runtime composition or for compile time composition, and they're effective in both cases. So our function pointers, now that we have done that, let's clean this up even further so that it doesn't eat into our text. Right? Our function pointers, they really correspond to cheap closures in a functional language. What you get is that there is a function that has no state, and that's essentially the only difference. There is no state. There are no other difference between these two. Okay? So that's the big message here, is that function pointers are a form of closure, but they're very cheap in a sense. Now, if there is no state, I'm already implying that real closures will have a reference to some state. And what is that? Well, it turns out that it's coming from what we call the environment. If you have taken our beloved 1729 as a CSE class, you know full well what that represents. The environment is the collection of names and their current binding to values that is in existence at the time you define something new. So if you are going to define a new function, before you define that function, you have a specific environment. It contains a number of names. They're bound to values. That's what you work with. And when you define the function, that function can capture any name that lives in that environment. And that could be anything in Scheme. When we're in C or C++, essentially we're going to talk about any name that would be available to you, like global variables, or really anything that's defined before the closure gets actually defined, right? So that's the big thing. And we're going to talk about that environment quite a lot, because in C++, the environment has some fundamentally different properties than in Scheme, since you can actually modify it. You have destructive assignments to make modification to the environment, and that is a big deal indeed. So our closures, just like in 1729 and Scheme, we're going to actually rely on lexical scoping. That is, you capture the values of the name that the function refers to at the time the closure is defined. And you don't keep a reference to the outside. So that's the basic idea of what I mean by a closure. If you think about it, there is this environment here, right? And that associate names to values. And you have a bunch of those associations. And at some point in the control flow, you're going on and you reach a place in the control flow where you're going to define a closure. So you'll say define closure here somehow. We'll see what the syntax is in C++. But when you reach the point of defining a closure, that closure is like a piece of Swiss cheese. It has holes in it. And the way we fill those holes is by picking up, because these holes are referring by name to some value of the environment. What we're going to do is take that piece of cheese and complete it, taking those holes and filling them up, right? The hole will be filled, the hole will be filled, the hole will be filled. And the filler is none other than coming from my environment. So the environment contributes the values associated to those names to plug in the holes in the closure definition. And therefore we get something that a beautiful function in the purest sense of the word. It does not depend on the outside. So that's what we mean by closures, and that's how we're going to actually make use of them. So this is our basic setup. Now, there are a number of questions, of course, such as what do we capture? Do we capture all the names in there? Do we capture the entire environment? Do we capture only some of these names? Which names do we capture? How do we control that? Well, again, in 1729 in Scheme, all of this was automatic, and you wouldn't have to worry about it. Here in C++, we're going to actually have to provide answers to these questions. They're very important questions. We need to address them explicitly. And again, that's for performance reasons mostly that we are concerned by this idea. So the second one is, when we capture, what do we capture? Do we make a copy of what's there and plug with a copy? Or do we actually make these things refer back to the environment, so that if the environment gets modified, the closure gets to see the modified version? In C++, with destructive assignments, we have to worry about that concept. Again, this is a subtlety that doesn't exist in 1729, which is a functional language, because over there, everything should be done by copy or by reference. It doesn't matter, because you don't have normally destructive assignments, and therefore you wouldn't be able to observe whether there is a difference between these two. In C++, that is not true. We have destructive assignments, so we need to be aware of that. So that's another big question we have to answer, and we'll delve into that real soon. The thing I want you to remember, though, is that simply a function pointer is a poor man's version of closures. There is simply no state. There is no environment. You directly have a function. There are no holes in it, except maybe reference to global variables, but that's it. There is nothing else. You don't need to refer to the environment at all. You capture nothing, which is why they are a little simpler to deal with. Being stateless is a bit of an advantage. Remember, by stateless, I only mean it doesn't capture anything from the environment except global variables. Global variables are always a special construction in C or C++. So that's where we are. And what we're going to embark on is really now start to take a look at how these things work. That is, how closures really do work in C++. And I'll see you next time.